This is the second lecture about a very important mathematical model, the harmonic oscillator model. You should have watched the video Harmonic Oscillator Part 1, and in that video I described the basic physical setup of a typical harmonic oscillator. There are other kinds of harmonic oscillators that occur in nature besides masses attached to springs, attached to walls or ceilings, but this is the easiest one to think about, and so this is the one we start with. We use Newton's second law, first of all, to write the force in terms of the mass and the acceleration, the second derivative of the position y. And we use something called Hooke's law to write that force in terms of y, ultimately resulting in a second order differential equation in the unknown function y. I simplify that equation by dividing both sides by m and introducing a new constant q, which represents k over m, and that shouldn't be forgotten. Ultimately, you should write your final answer in terms of k and m if it involves a k and m to begin with. I didn't really do that in the last video, but I'll show you how to do that here. And the method that we used to solve this second order linear equation was guessing. Guessing doesn't always work, just in case you're wondering, but it does quite often work with linear equations. And cosine of square root of qt and sine of square root of qt were two particular functions that solved this particular equation right here. They're not multiples of each other, so a general linear combination of those is the general solution. An arbitrary constant k1 times cosine of square root of qt plus another arbitrary constant k2 times sine of square root of q times t. To solve initial value problems, you need to find the derivative and set the original function and the derivative equal to whatever constants you have over here at a specific value of time. Usually it's t equals 0, though not always, but if you imagine what could happen if you use some other value of t, like pi over 6 or something, or even something that's not a multiple of pi, like 3 or 4 or 5, you would get pretty nasty equations involving k1 and k2. In this particular example that we did, the equations turned out nice. There was our particular solution to the initial value problem, y equals cosine of square root of q over square root of q times t. In terms of k and m, that would be y equals cosine of square root of k over m times t. And you could write your period and your frequency in terms of k and m also. The period, which I'm calling capital T, if I plug in q equals k over m and then rearrange the fraction, I could write the period as 2 pi times the square root of m over k, and m over k because the q is in the denominator of the original fraction, and q is k over m. And the frequency, 1 over the period, can be written as 1 over 2 pi times the square root of k over m. Would be the frequency. If you're thinking about units, the period would be in seconds typically, if time is in seconds, and the frequency would be in 1 over seconds, which is sometimes called hertz. There's also a concept of something called an angular frequency, sometimes denoted with the Greek letter omega. That's not a W, that's an omega. And the angular frequency is really the same as the frequency, but multiplied by 2 pi. Just square root of q in terms of q, and square root of k over m in terms of k and m. The units for that would be in radians per second. It's a little confusing because there's really no angle going on in the picture, but it's useful to think of the units as radians per second anyway. and it is sometimes a useful quantity to think about. I also introduced you to the idea of the system perspective for this differential equation. The system that you end up getting, the first equation in the system looks like this: dy dt equals v, where v is going to represent the velocity. That differential equation just comes from essentially defining what v is. It's the rate of change of the position. The second equation in the system, dv dt, is the same as the second derivative of y. I'm just differentiating this equation. But the second derivative of y is equal to negative q times y, or negative k over m times y. That's your second equation for your system. So we think of these two equations as a first-order system. And solutions to this system ends up being a parametric curve. You can think of that as a point moving around in the YV plane. It's an ordered pair. That one ordered pair would be a solution. It would be one function if we solve an initial value problem. If we want the general solution, then it's really infinitely many functions. But we want to think of it as being an ordered pair, and we want to draw it as a parametric curve in the phase plane. And we saw that these particular curves are going to go around clockwise if I label the horizontal axis with y and the vertical axis with v. On the CD-ROM, they labeled it the other way around. The vertical axis with y and the horizontal axis with v, because of the fact that on the CD-ROM, y was representing a vertical position, whereas I've drawn y to represent a horizontal position. And in that case, it went around counterclockwise, but it really is still representing the same motion of the mass and the spring. I'm drawing these to look like circles, but they're not necessarily circles. In general, they are ellipses. The particular solution that we got last time was little y of t equaling cosine of square root of qt, and v of t equaling negative square root of q times sine of square root of qt. And I mentioned that the parametric curve that this generates lies along an ellipse. I'm going to verify that now. What ellipse is it? It's the ellipse defined by this equation: y squared plus v squared over q squared equals 1. That's the equation of an ellipse in the YV plane, with y-intercepts at plus and minus 1, and v-intercepts at plus or minus, well, this should actually be just a q here, not a q squared, plus or minus square root of q. Q is positive. I need to verify that I'm always on this ellipse. So essentially all I need to do is I need to take these functions and essentially plug them into the left-hand side. Plug in cosine of square root of qt in for y and square it. Plug in negative square root of q sine of square root of qt squared. Plugging that thing in for v, I'm squaring it because I squared the v, divide the whole thing by q, and now simplify. And the key fact, after canceling the q's, which I get with squaring negative square root of q, I get another q on top which cancels with the one on the bottom, is that I have something that I can simplify via the fundamental trigonometric identity that cosine squared of something plus sine squared of that same something always equals 1. As long as these two things match, which they do, this is going to equal 1 no matter what t is. So this will always lie on that ellipse that's defined by this equation. Doesn't guarantee that it definitely goes all the way around the ellipse. That has to be seen by thinking about what the graphs of these things look like and how they behave. But it definitely always lies on top of that ellipse, no matter what t is. think of this equation, this system, in a new form now. In fact, this is the main topic for this video. I want to think of this in vector form. And in particular, I want to think about how you can visualize what phase plane looks like without actually even drawing in solution curves initially, without actually even finding them. Essentially, the main topic for today is the idea of a vector field. And I'm going to relate it to the harmonic oscillator. I haven't made the following kinds of videos yet, but maybe I have by the time you're watching this. I may have made videos related to looking at biological models, ecology, and in particular what are called population models like predator-prey, competing species, cooperative species, and I probably have looked at phase planes and vector fields in that context too. I'm going to look at vector fields in the context of the harmonic oscillator right now. Essentially what a vector field is it's a function. In books they'll make it with bold-faced letters. I can't do boldface with chalk or with pen. I suppose I could try, but for the sake of time I'll do what many teachers do and put a little vector symbol above the letter. It's really a half vector symbol. Vectors are arrows. You might see people put a full arrow, but just for the sake of time I usually like to put half arrows, as many teachers do. It's a function that takes a vector as input and gives you a vector as output. So we think of this vector y as the input for the function. Think of f as the function name, and therefore f of y as the output of the function. Vector input, vector output. You can think of the inputs, when you say vector input and vector output, you can think of the inputs and outputs either as points or vectors, because there's an association between any point in the plane and its position vector. Draw a point in the plane, no matter where you pick it, that point has an associated position vector, the vector that goes from the origin out to that point. And essentially we don't always make a distinction between a point and its position vector. So I'm free to think of these things in either way. And in fact, the usual thing to do with vector fields is to imagine the inputs as being points and the outputs as being arrows, as being true vectors. And we will graph the outputs, the arrows, to be based at the inputs, the points. Here's an example of a vector field. If I think of capital Y as representing the point y comma v, I'm putting extra parentheses in there, but just this one time for emphasis. We usually won't bother with the extra parentheses. I did it here to emphasize that it's a point, whereas these outer parentheses are just specifying that that's the input of the function. That's going to be my input, my arbitrary input, y comma v, and my output is going to be v for the first component of the output and negative y for the second component. I'm writing both of these as points. This one you do truly want to think of as being a point, but this one I'm going to want to think of as being a vector, an arrow. If you prefer the notation used in physics, the first component is a multiple of I hat, the unit vector, along the x-axis, pointing in the positive direction. And the second component, negative y, is the multiple of j hat, the unit vector that points upwards along the vertical axis. Unit vector meaning vector of length 1. You might be more used to thinking of it that way. I won't typically do that in here, and neither does the book. But initially here, if that helps you think about the output, go ahead and think of it that way. I want to graph this vector field. in a YV plane. What you do is you pick a bunch of points, pick a grid of points, and think of those points as your input, and then draw arrows based at those points with these components as your output. A good grid to pick might be starting along the y-axis, where those dots are 1 unit apart, then going up along the v-axis. These are all 1 unit apart vertically and horizontally. This, for example, is y equals 2. This is v equals 2 up there. -2 down here, -2 over here. Think of those as your input points into the vector field. Let's take as an example this point right here. Y equals 2, v equals 1. If y equals 2 and v equals 1, then my output vector has first component 1 and second component -2. I would write f of 2, 1 is 1, -2. So at the point 2, 1, I draw a vector, an arrow, with a horizontal displacement of +1 and a vertical displacement of -2. So it's an arrow moving to the right by 1 unit and down by 2 units. It would look like that. Let's try f of 2, 2. Based at this point. Y is 2, v is 2. I'm going to get an output of 2, -2. A horizontal displacement of +2 and a vertical displacement of -2. It's going to put me right about there. You can see, even though this is, well, I think it's kind of fun, it will take a while. See how fast we can do some more of these. Take this point, y is 2, v is 0. The output is going to be 0, -2. This point is 2, -1. The output will be -1, -2. Think about that. Y is 2, v is -1. I'm going to get -1 there and -2 there. A horizontal displacement of -1, so now it moves to the left by 1. And a vertical displacement of -2, it's going to give me an arrow like that. This point, y is 2, v is -2. I'll get an output of -2, -2. It'll put me down here. Let's go back up here. Y is 1, v is 2. I get an output of 2, -1. That's going to be a vector about like this. This point, y is 0, v is 2. 2, 0 is my output. Y is -1, v is 2. 2, +1 is my output. Over here, y is -2, v is +2. I get 2, +2 as my output, etc. Let's try one more. Let's try one with coordinates. Let's do this one, 1, 1. Y is 1, v is 1. I'll get 1, -1. There's my output vector. We're starting to see a general pattern here, at least, and I could take more time to finish this. I won't do that. The key pattern to see is there's sort of a clockwise rotation. And in fact, that clockwise rotation is mimicking what the solution curves do. We saw that solution curves rotate clockwise. And if I've truly picked the q from the differential equation to be 1, I will actually get true circles here for solution curves. There's one solution curve. Here's another one. This is supposed to be a circle. They will go around clockwise. And they essentially follow the vector field. In a loose sense, you might think that initially. But they follow it in a real precise sense, too. They follow it in such a way that any time one of these solution curves passes through the base of one of the vectors in the vector field, that vector is not only tangent to the curve at that point, but its length gives you the velocity of the curve at that point. When you've got a point moving around a curve, it's got a natural velocity, a rate of change of distance traveled with respect to time. I guess I should say speed, excuse me. It's got a natural speed, a rate of change of distance traveled with respect to time. The length of the arrow when it passes through the base of that arrow is the speed at that instant in time. Therefore, it makes sense to call these arrows the velocity vectors of these solution curves. They point in the direction of motion at every instant that a curve passes through the base of one of those vectors, and the length of that vector that the curve happens to be passing through at that moment is the speed of the curve at that instant in time. Why does that happen? The differential equation, the system, can be written in vector form. Essentially, this is a shorthand for the following system. dy dt equals v, and dv dt equals negative y. If I take that system of two scalar equations and think of it as a single vector equation, with dy dt in the first component, dv dt in the second component on the left-hand side, and the right-hand side equaling v for the first component and negative y for the second, this is a shorthand way of writing that. Look at the right-hand side here. V for the first component, negative y for the second. That's the same thing as what I've got here, v for the first component and negative y for the second. Written in a different way, written as a column vector down here rather as a point up here. But in this textbook, we don't really make a distinction between row vectors and column vectors. There are other situations where you do want to make that distinction, like in a linear algebra course. But in this particular differential equations course, we don't worry about that distinction. We think of these things as equivalent things. And when I write it in this form, not only is it a convenient shorthand, but it also helps you understand why the solution curves follow the vector field. Because what it's saying essentially is this. The derivative of a solution curve, which will give you the velocity, at any instant in time, is equal to the output of the vector field at that point you happen to be at that instant in time. I'll say that again. The derivative of a solution curve, which will give you the velocity of the solution curve at any instant in time that you want, equals the output of the vector field for the given point that you happen to be at that instant in time. That's essentially saying the same thing that I said here visually, that any time a solution curve passes through the base of one of the vectors like this point, when little y is 0 and v is 2, the velocity vector of that solution curve at that instant in time is the same thing as the output of the vector field. That's the output of the vector field at y equals 0, v equals 2. That vector right there, and it's the same as the derivative of the solution curve at that point. That's a very, very fundamental thing for this course to realize that. We will use that all the time. In fact, you will get to the point where you essentially use it without even thinking about it. Very, very essential. That's my introduction to vector fields in the context of harmonic oscillators. I'd like to end by enticing you to think about harmonic oscillators in other situations. Does it seem bright enough? Maybe I can make it a little bit brighter. Zoom in on that. When we get to chapter 4, or when you get to chapter 4, we're going to consider harmonic oscillators where there's external forcing. If you go to forced mass spring, you can play with that kind of situation. So here we have a mass on a spring again. Vertically, the effect of gravity has been taken into account by essentially shifting where the equilibrium would be. We have the ceiling up here, but you'll notice there's a little extra piece here. That's going to be what is the external forcing that will drive the mass to move in strange ways. Down here we've got some kind of damping. Maybe you imagine this is a tube filled with water or something, and you've got this extra piece that goes down into the water, and so that causes some damping to come into play, some friction essentially. I'm going to set the damping equal to 0. That's the slider at the very bottom. I can move it to right or left. If I move it all the way to the left so that B is 0, then that tube goes away. There's no more damping. So now I'm pretending there's no external friction. Over on the right here, you see an F and an omega. F essentially measures the magnitude of the external force, and omega essentially measures its frequency, or you might say its angular frequency. Notice that I've set M and K to both be 1 here. That would mean Q will also be 1. Let's initially set that external forcing to have a force of 0. So I'll set F back down to 0. That's the situation from the last video where there really is no external forcing and you get periodic solutions. You see the position in red here. I can also add the velocity. In blue, that will be the derivative of the red one. It's a bit tough, but you can try to follow the point over on the phase plane here. So the red curve, it's easy to follow. That's just the up and down motion of the point. It's moving kind of fast here. The blue one is the velocity. That's measuring the horizontal position of the point in this phase plane as it's labeled y vertically and v horizontally. If it were labeled the other way around, then we'd have to switch our perspective. Let's now stop this and add some external forcing. Watch what happens if I set the external angular frequency equal to 1, which is the same thing as the square root of q. Q happens to be 1, so the square root is also 1. Watch what happens. I'm going to start the mass real close to 0, but not exactly equal to 0. Watch what happens. So I got this external forcing going on up here. And, well, it looks like the spring should break, but it doesn't. This is a computer simulation, so the spring doesn't break. What in the world's going on here? Essentially, the external forcing and the spring, Q, as related with the, well, actually with K and M, are in perfect unison in a sense. They are in resonance. And essentially, it's causing this to go wacko. It has exploded. Of course, the spring would truly break in real life. We see perfect resonance here. If I stop this, clear it, and set that external angular frequency to something slightly different from 1, we'll see something pretty similar. It will go pretty wild again, I think. Yeah, it should. It's near resonance, but we'll actually see that because it's not quite exactly at resonance, we'll see something interesting happen. Because they're off a little bit from each other, these frequencies, it should do something else. You see it doesn't go too wild. with enough patience here, now you can see it happening. It's starting to slow back down again. The fact that those frequencies are out of phase a little bit causes this to happen. But once it's slowed down enough, it gets to a point where it goes back to oscillating with very big oscillations again, and the cycle would repeat itself. This is called beating. It's a beating phenomenon, and we'll learn about it in Chapter 4 and how to analyze this. And that's the end of this video.